Okay, so last time we talked about thighs, meat, and prosciutto. No, this isn't exactly what you think it is if you're new to this course, but these are constructs or these are mathematical objects which we showed to be homomorphic to, if I remember correctly, the circle, the disk, and I mean the sphere and sphere, the disk, and no, this one's a disk. This one's an open ball. Yeah, so it's the sphere, the ball, and the disk. So thighs usually are homomorphic to some Sn. So an n thigh is equal to Sn, or is homeomorphic to Sn, and an open meat is homomorphic to the n ball, and a prosciutto, an open prosciutto, is homomorphic to an open disk, and a closed one is closed prosciutto is homomorphic to a closed disk. So this is what we discussed last time, and we also talked about their fundamental groups. So today, or in this lecture, this is gonna be a hallmark lecture, or a very important lecture, because in today's lecture I'm going to be finally proving the Van Kampen theorem. Okay, so this proof is gonna be very important. If you guys are asked why exactly the Van Kampen theorem is true, you guys are going to want to bust out this proof. So, let's revisit the Van Kampen theorem. What does the Van Kampen theorem say? So, let's rephrase the Van Kampen theorem into a more general one, okay? So, let A alpha bracket be a collection of open path connected subsets that cover a space X. So what we mean by it covers a space X is that if I take their union, their finite union, I will get X. Okay? So that's what we mean by it covers X. Okay? With each X naught. So base point is X naught, is inside one of these. Yeah. That's not how I'm trying to get used to writing how we usually write the naturals. Okay. So the base point of our space, because when we construct our fundamental group of our space, we want to also consider base point, where all the elements of the fundamental group is based at. So where they all start or where they all end. Yeah. So, yep. We need the base point, and it needs to be inside one of these open path connected subsets of our space that we want to find out. So, in terms of our theory, of course, if I have a subset of F here, femboy space, I have a bunch of groups of, not really groups, but subsets of them. Like I have collections of those femboys that are open, so they are there, but they're not bounded by some femboys, okay? And then the base femboy which we base all our, you know, linings of femboid, or very fine lines of femboids, which make up our fundamental group. It starts at that one femboid, okay, and ends at that one femboid, of course. And that femboid is inside one of these, or maybe all of them. It could be part of all their intersections, for all we know. And so yeah, so note that this isn't a line now, like we discussed about curves and elements of the fundamental group, but this over here is a shape inside, so it's a subspace of space X, or yeah, subset of our space X. So of course this would imply subspace topology, but that's not our concern for now. Okay, so I have an embedding, so let J alpha be an embedding from any of these subsets onto X. So originally these subsets are, I mean, you could say they are inside X, but we cannot say that they're originally inside X. Well, one, we have no sense of time in topology, and then we cannot tell when we took the subsets out and then claim them to be subsets. We just said they are path-connected subsets. So the notion of embedding or putting them inside X is independent of time. It can happen anytime. It can happen before we even define this or after we defined it. So it doesn't matter. So what matters is that I have an embedding J alpha, and I have a corresponding embedding. So I take my group of femboids that we say to cover X, right? So they're not precisely the subsets of X, but when we put them together into one singular set, they become X. I'm gonna put one of these inside X, okay? So it's probably gonna get absorbed with its, you know, original version inside X, but that doesn't matter. Okay. So that and the corresponding thing that embeds. So this time I have an I, alpha, beta, that embeds the intersection of some A and A beta. So A beta is part of this collection of open path connected subsets that cover X. Okay. So still same notion of a collection of femboids, and then we take the intersection. So the femboids that are inside both of them, okay, but not the ones that are in one that are not in the other, and vice versa. Okay, so I have a corresponding map that embeds this intersection into A alpha. So I take the intersection of both of these subsets that cover X, or that is part of a cover of X, and then I embed that, I put that inside A alpha. So we just sort of stuff it into A alpha. Okay, so I have another map. So just a little note, so this big asterisk that I'm gonna write later, that's indexed. So we're gonna copy summation notation, and we're gonna define this to be some alpha, okay? So asterisk sub alpha, okay, of A is just the free product of that set A alpha amount of times, or n amount of times. So A is indexed by alpha, and then I have some alpha equals 1 to n. Of course, this could just be shortened out to asterisk and then n, or asterisk alpha of A, and that would be the same thing. We're just sort of indexing it instead of fully expressing it, so it's not as cumbersome as writing it full out. Okay, so that's the general free product of our index sets A alpha. Okay, so I have a map. Okay, embeddings. So these two are embeddings. Okay, let big psi, big phi map multiple free products of are fundamental groups. So the free product is an operation between fundamental groups only, not the spaces themselves. Okay, the fundamental group pi1 of A alpha, and then at base fanboy 0. And say that maps it onto the fundamental group of X. And you can already see that this homomorphism or isomorphism, if these two are exactly the same, is a more general version of what we originally said. Okay, and the precise homomorphism is that I take the quotient group between this and the smallest normal subgroup we can construct, and then we get this. Okay, and then just make an equivalence relation with that. Or rather, it's the quotient set, or not the quotient set, the quotient group between this and its smallest normal subgroup. Okay. Okay, B, so let that be the extension of J. Let's see if I didn't miss anything. J alpha star. So if J alpha embeds this space into X, then J alpha star embeds the fundamental group of this into the fundamental group of this. So that's this phi here is an extension of this J alpha star, which embeds the fundamental group of A onto the fundamental group of X at base point X naught. Oh, sorry. Embed. It's an embedding, not really just a regular map. Or not a homomorphism. This is an embedding between two groups. Okay. Okay. So, all right. So this is our restatement of. Oh wait, no. We have two bullet points here. So one. So these two letters I and II are what we're gonna prove today. And because we've proven that, we've essentially proven this fact or this theorem, and effectively have proved already what we've used in the previous lectures. Okay, so this will require a little bit of stretch of imagination, and we will be using a bunch of pictures today. But nonetheless, that's our goal today. Yeah. Okay, so if each intersection between two of those subsets that cover X is path connected, I'll show you the PC, then the kernel of big phi is surjection. Is a surjection. Oh wait, no. Yeah, is it? Wait. Oh wait, no, sorry, wrong. Is path connected? Then just phi is a surjection. Sorry, the kernel cannot be a surjection. The kernel is a set, not a mapping. Okay. So if these two intersections is path connected, then big phi is a surjection. Okay. So a surjection means, of course, we're mapping a smaller set into a bigger set. So, and that's obvious because A alpha here is just a smaller space that's a part of a set of spaces that we say to be a cover of X. So therefore, it is immediately smaller than X, and because of that, even if we generate a free group over a bunch of curves inside it to generate its fundamental set, that would still be smaller than every possible curve we can construct in order to make the fundamental group of X. So A is fundamentally smaller than X, and so even if we take the free products of this, it would still be somewhat smaller than X. Okay, And so that means that we're mapping a smaller set onto a bigger set, and so it's a surjection. Now I know there's another way of showing or saying that it's a surjection, a more formal and less, hand wavy formalism, but I won't go much into it today except for when we do the proof. Okay. So to the second bullet point, I may need to erase this. No, I think I can erase it. If each, so we have a tri-intersection. So alpha, A alpha intersect A beta intersect A gamma. Okay, A gamma is PC, is path connected. Then the kernel, this is where the kernel is actually at, not the first bullet point. Then the kernel of big phi is the smallest normal subgroup containing. It's the smallest normal subgroup containing I alpha beta star of F, and then concatenate I beta alpha star of F to the minus 1 for all alpha beta and F. Oh wait, no. I believe alpha beta is inside the index set of these sets. Okay, yeah. So it's not N, but a alpha is part of an index set J. So alpha beta is a part of an index set J as well. Okay, that's a J, not a. Okay, and F is inside the fundamental group of the intersection of A alpha and A beta. So when we show this, right, you'll notice that the Van Kampen theorem is a sort of extension of the first isomorphism theorem, in which these three products is our original thing that we want to prove to be something. The image of this is precisely the fundamental group of X, which we want to find out, and the kernel of phi is that smallest normal subgroup. When we need a normal subgroup to mod by, right? That would be a normal subgroup of this entire thing. And so when we mod this out by the normal subgroup, we would get the image of this homomorphism, which holds true by the first isomorphism theorem. So there it is. So this is sort of an extension into algebraic topology, or it's an application of the first isomorphism theorem in the context of algebraic topology, and by another extension, R theory. Okay, so I guess, yeah, there's not much to visualize here. Of course, this here is a triple intersection of spaces, so I have 3 collections of femboys, and then I find out or take all the femboys that are inside all of them. And that's what we're taking into consideration in the second I here. Okay. So now that we've stated the theorem, let's get on to proving it. And yeah, I should have warned you guys at the start that this is going to be a very grueling lecture. So grab a water or something, and then yeah, grab a water or a snack, but mostly your notes. But yeah, and let's start this. So we're gonna prove the first one first. We're gonna prove I first. We're gonna prove I. Okay. First. So proof. proof of I. Oh wait, no, we're proving the entire thing, and then we're proving it by section. Okay. Okay, proof. So one, I'm gonna make now a map, or I'm gonna take a curve 0, 1, or a path 0, 1, which is f 0, 1. I'm gonna say given f that maps 0, 1 onto our space X. So I have a line of femboys and I'm gonna embed it inside X here. You know that. Okay, a loop in X. So it's a loop. So it's a loop in X based at X naught. So you can already probably tell that this loop might be a member or an element of the fundamental group of X. That's one thing you might observe or you might suspect, because it's based at X naught, right? Our base femboy. Or yeah. Okay, there is a partition. So I'm gonna let you guys work out the math on this one, but there is a partition. There's a partition of the interval, which is, I'm gonna extend a little here so that you guys, I have more space to write it. So 0 is equal to T0 less than T1 less than T2 less than less than TL equals 1. So the reason why 0 is equal to, or this first interval is practically the same as this interval is because is this interval 1 and this interval is 1, because of course we're making a loop, so it's sort of it goes around. So it's like a circle, somewhat homomorphic to a circle practically. And of course T alpha or Ti, however which way you're going to index all of these elements are the parameters of Rf. Okay, so each T is taken from 0, 1, wherein T0 is 0 and TL is 1. And the reason why it's L is because length, basically. Okay, so there's a partition such that F maps this interval. So the interval, closed interval Ti plus 1 into a single A alpha. So this is our claim. So this is what we're actually going to prove for the first one, or first section of our proof of the Van Kampen theorem. So what we want to show is that there is a partition of the interval, this interval, such that F maps this interval, any two of these. So any two consecutive pairs here, so let's say 1 and 2, into a single A alpha. So these T's over here are femboys, and then we take two pairs of femboys, or two pairs of femboys, and map them onto a single, or inside. Maybe you say it's an embedding, but I won't say it's an embedding just yet, because when we say it's an embedding, of course, the elements we put inside the other set will absorb or have their properties replaced by properties inside there, or they will start to have the same properties inside that structure. Otherwise, if the structure has elements or new elements it takes in from an embedding, and the elements don't conform with the structure of the thing, it's of the set or the structure, then the embedding was meaningless. Because the embedding would imply, of course, that the structure of the group would be followed by the elements. Okay. Or not the group, but the structure of the structure. Okay. So, denote A alpha corresponding that F maps T onto I'm gonna index that or denote that entire interaction as the following. So after I ti plus 1 as a sub I. Okay, so each when we do the partition and then f maps those things, or sort of not really embeds but just maps them into that a alpha, right? These two are related via this f. We're just gonna denote it, that entire interaction, all that entire mapping, as ai. Okay, not the partition, but when f maps this interval onto a alpha, we're gonna denote by ai, a sub I. Okay. Yeah, we're 25 minutes already. We have 1 hour. Okay. Let. So I'm gonna use compact notation so I have more space to write the proof. So let f sub I equal or be the restriction of f to the interval t sub I plus 1. So, alright, restriction. So we're just applying the map over these two. Okay. Now this f here ranges every possible value in this interval. Okay. So it ranges over every possible value here, and we're restricting it to this specific thing that we map onto this a alpha. So we're focusing on one map and on a singular interval being mapped onto a singular subset that we claim to be a part of what covers X. Okay. For each I, so for each index I, pick gi, which is inside the intersection between a sub I, intersect a sub I plus 1, a sub I plus 1, from x naught to f sub, or f of t sub I. Okay, so for every I that we pick, over here, we pick some element inside the intersection between, this interaction or this correspondence. So this g sub I is a map itself. Okay, so we find similar maps between this mapping or this correspondence and this correspondence. So for this correspondence, this time it would be mapping t sub I plus 1 and t sub I plus 2 onto a alpha, or a new a alpha that isn't the previous one. And that map would also take, or for each index, right, we're going to pick a map that takes x naught to f of t sub I. So whatever, we're essentially mapping these two elements onto two separate elements in a sub alpha, or both of them onto one singular element. It doesn't matter. What matters is that the image, so the base femboy is taken. So if I get the base femboy in X and then put it through G sub I, it takes that onto, the image of this femboy here. So what this femboy is, or what his position is, or whatever the heck he is, inside A alpha after we perform F. Okay. So once I pick that, F is homotopic to the loop. So I think that's F. F1. Okay, it's F. F is homotopic. So F is homotopic to the loop. The loop F1 concatenate G1 inverse. So recall our definition of an inverse in the last time. This line on top of the mapping. That is an inverse. Okay. Concatenate G1 concatenate F2 concatenate G2. So this string over here is a map, okay? Not an object, not a subset or whatever. It's a map, or it's a loop actually. These are loops, and then we compose them together, concatenate them together. Okay. And then that's dot followed by multiple concatenations until we get to GL minus 1 and then F sub L, whose constituents are all based at x naught. So it would make sense, of course, because each of these loops, every single loop that we ever have considered since the start is based at x naught. Okay, so at the start of this lecture at least, or this proof. So it would make sense that every possible thing that we can construct, right, from these things are all based at x naught as well, unless, of course, we specify that it's not based at x naught. Because unless we specify it's not based at x naught, it's already sort of intrinsically stated, I think, or it's already a given that they're based at the base femboy x naught. Okay. Okay. So note that I must note. So let's note that note F1 concatenate G1 inverse is an element of A1, and then G2, G1 concatenate F2 concatenate G2 inverse is an element of A2, and then and then GL to the minus 1 concatenate FL inverse is an element of AL. I know it looks like an E, but it's supposed to be like the italicized L that we use in LaTeX. So it looks somewhat like this. It's L in LaTeX. Italicized L. It's literally spelled ELL in in LaTeX, or in the environment when we incite it. Okay. Since each, let's move to the next page. Since each factor, so this is one entire loop, right? And these little constituents are part of these, little subsets A1, A2 up to AL are factors. These guys are factors of this entire loop. So I know it's a bit abstract, but think in terms of I decompose these loops, or these very fine lines of femboys, and I put them together, and then I have this entire thing, F1, G1 inverse, G1, F2, G2 inverse, GL to the minus 1, concatenate FL. Okay, so since each factor stays in a single A sub I in their respective A sub I, this shows F is the image of phi. Is equal to the M of big phi. And so that ends the proof. Alright, so there. That's our proof. So I have a loop, any loop that you can think of in X, based at our base femboy. There's a partition of the interval such that F, our original function, maps two parts or two femboys inside our interval femboys into a single space that we claim to be a part of what covers X. So we put them inside the subset. Okay, denote A sub I corresponding to these two are, so that relation that we did where we put those two single femboys into a subset that covers X, or one of the subsets that covers X. and we denote that by a sub I. And then we denote again f sub I to be the restriction of our original function f at these two femboys. Okay. For each I, we pick another map inside these that's an intersection that holds the same structure as these two, as an a sub 1, a sub I, and a sub I plus 1, that takes the base femboy to some new image f sub t sub I, or whatever this function does to any t sub I in this interval that we chose in the beginning, right? Those two femboy specified femboys those two special femboys that we chose to map inside a sub alpha. And what exactly this looks like in a sub alpha, G sends x naught, or the base femboy, onto what that femboy looks like when we send it to a alpha. Okay, and so because of that, f is homotopic to the loop, which is this entire string of maps. Okay, so that G I, which holds the same, which is inside the intersection of those two relations. So still a loop, f is still a loop, and then each of these index fi, which is a restriction, and then we put them together, and whose constituents are all based on x naught, of course, because every single thing we've done up to this point, because of course f comes, or the relation between a sub I and these two femboys, special femboys, is from f, basically. From that partition we did. Now we don't want to focus on the partition. We want to focus on what happens to the primary loop, or map that that loop stuff. And so, yeah, it all traces back to this singular point here that tells us that this f, this map here, or this loop, is based on x naught, and it stays throughout all. It stays like that all throughout, except for this G sub I, or this index family of loops or maps that sends at least x naught to this new image of T sub I, which is what T sub I looks like, or the femboy T sub I looks like when we map it onto a alpha. Okay, so we note that each of these individual ones are factors of this big, large loop. Okay, and they stay in their individual things no matter what we do to f. Okay, because really there is no maps here, or there's nothing that we modified in f at all. So these guys stay the same. And when we do make a corresponding change in f, let's say we make another construction f, and then say it's homotopic to f, and then send every single thing that we've done here to that homotopic loop, then there's a corresponding change here, such that these guys stay in their respective neighborhoods, or change neighborhoods. Neighborhoods also change, and so they don't change at all. Okay, and since each factor stays in their respective a sub I, which I just said right now, this shows that our f, or family of subsets that are essentially the constituents of the fundamental group, or the fundamental group of our subsets A alpha, is precisely the image of our primary homomorphism big phi. So that's the first section of the proof. Grab a drink or pat yourself in the back if you still understand this mess. I know I was so dejected, and so it was a bit hard for me to understand first. So grab a drink, pat yourself in the back, and maybe pause the video, take a deep breath, and think yourself that your brain hasn't exploded at this point. I know my brain has when I first heard of this proof. And so here's when things get a little bit tricky and will require a little bit of ingenuity and imagination, right? So yeah, love interest is very, very imaginative, and frankly, I think that love interest would. I think his brain would explode if he saw whatever hell I'm doing right now. Okay, so, okay, now let's prove 2. So the second one. Right. Now I'm gonna change my marker, and then we're gonna continue the lecture. Okay, so we changed it. Okay, looking fresh. All right, the second one, by a factorization of f, which we just did a while ago, we mean a word on the free product. On the free product, which is possibly unreduced. And we'll get to that, what exactly this sentence means. Which is mapped by big phi to collection. So remember our factorization a while ago, you know, the f sub 1, g inverse, stuff like that. Which stays in the respective covers of X, or respective subsets of the cover that covers X. We mean a word on the free product. So I take the free product of any of those two. The free product was already defined in the previous lecture, and I take a word over that. So I string concatenate them, or I just concatenate them together. So I take the free product of every factor of f, right? So, and then I take a word over that. So I concatenate them further. So free product could be a concatenation, but it's not really a concatenation. But once we take the free product, that's when we take a concatenation. And that's what we mean by a word, which is possibly unreduced. So we cannot shorten down, or we cannot shorten the notation for a femboy here, which we could have done in a previous lecture. For some cases, of course, and which is mapped by, you know, this big phi onto f. Okay, so big phi does many things other than map the fundamental group of the free product, or the free products of our fundamental groups of the covers, or the subsets of the covers that covers our original space, and, you know, onto the fundamental group of our space. Okay, it does more than that. So we're sort of mapping out what else it can do. Say that 2, so now we say that 2 factorizations are equivalent, and factorization could also mean decomposition via free products. So we decompose our map or whatever into a bunch of little tiny subsets that are whose free product is precisely f, but that's not focus. Okay, so we say that 2 factorizations are equivalent if you can get to one, so you can get to one from the other by a finite sequence of 2 steps. So this is a definition for now, okay? So this is not, we haven't gone yet into the proof for number 2, so we're starting off with the definition. Most proof starts with a definition, of course, or they employ a lot of definitions in order for them to work. Okay, so the first number, is that combine any 2 fi and then collection f, okay? So equivalent classes of f under our very, very early notion, right, in constructing the fundamental group, which is concatenation, of course. 2, this singular string, f sub I, concatenate f sub I plus 1. Okay. If they are elements of the same fundamental group. So if Fi and Fi plus 1 is inside the Fermat group of A alpha, or at least their equivalent classes as well. So it absorbs other similar groups. Just like how, of course, equivalence class of integers absorb, negative integers in order to construct our quotient group, of course, right? Yeah, our quotient between R and left cosets of R. Okay, so right, if they're if they're elements of the same fundamental group, of course this is a group, then we can combine these two into a concatenation of themselves, and then take the equivalence class under concatenation, and then yeah, so we can combine them. If these two elements of this fundamental group or if these two elements are inside the same fundamental group, we can essentially split it into the equivalence class under concatenation of the concatenation of the first loop and the second loop. Okay. So it's sort of an absorbing property. Okay. So I have a bunch of loops that are similar to these two under string concatenation, or not just concatenation. And then, because they're in the same fundamental group, I can just decompose them. It's somewhat like multiplication, if I believe, or addition. We are applying abstract algebra into topology in order to explain these, or in order to study these structures further. Okay. So the second step, if an Fi equivalence class inside pi 1 of A alpha is the image of pi 1 of A alpha, A beta, then we may consider as an element of A beta. I'm sorry if my handwriting is a bit trash here. Let's write element better. It's an element of A beta. Still trash, but you guys get the idea. Okay. So we are now tantalizingly almost close to the proof. Okay, so these are 2 steps. So 2 factorizations of f are said to be equivalent if you can get to one from the other by a finite sequence of 2 steps. So these 2 factorizations, fi and fi plus 1, or at least their equivalence classes, you can combine them into an equivalence class of their concatenations. The concatenation is the original loop, which is, say, the other loops are similar to, if they are elements of the same fundamental group, of course, of this singular, or any of these subsets which cover X. And the second one is that if our F, or equivalence class of F sub I, is inside this fundamental group, or that fundamental group, is the image of this mapping, from, the thing onto its fundamental group. I mean, this is essentially all mappings, right? Because they're collections of mappings, right? Then we consider it as an element of A, or A alpha, A beta. Okay? So, the second step does not change the class of the word in Q, which is equal to the mod of the free products of all these alphas. So, A alpha can be also, in this following statement, A alpha is an index. And also we're out of the definitions now. We're already actively proving this thing. Okay. So, the second step a while ago doesn't change the class of the word in Q, which is the free products over all alpha of I1 A alpha. So the free product of all of these fundamental groups mod our smallest normal subgroup N. So what we have to do is show that any 2 factors of a given equivalence class F is this, which is a subset of f1 of the pi 1, or the Fundamental group of the entire space, are equivalent. Okay. So suppose the Fundamental group, the equivalence class of some loop f can be factored into f1 fl, which is equal to the equivalence class of f prime, or f1 prime equivalence class of fk prime. So I'm sort of changing the index or the denotation a bit. Okay, with each f sub I, f prime sub I, a loop in A alpha, there is a path homotopy f, big F, that maps the interval or the cross interval 0, 1 cross 0, 1 onto x. So this is a square, right? This is a square onto x, or at least two elements from that, and takes them to x. Okay, such that f of 0 indexed by t is equal to f1 up to fl, all composed at t. And f of 1 t is the same thing, but it's all the primes, or all those, the prime of those elements, which are practically the same, though I don't. So this is a sort of formalization of our previous statement a while ago, right? It's similar. Okay, so all the compositions of those f primes, 1 f k at t. Okay, but the same compactness argument we can partition So we're using the same argument in improving the first one, and we're gonna partition this interval I1 cross I1. I mean 0 to 1 cross 0 to 1. Okay. So you notice that it's similar in a way to the loops a while ago, or in number 1 a while ago, wherein we had some map, small f, that takes 0 to 1 onto x. So this time, this one here is like a, I guess, it's a space of points that we map onto x. So there's a partition. No, we can partition each interval. So we're essentially using the same argument for proving number 1 to prove number 2, or II basically. So this time, instead of femboys, we have loops of femboys now. Or no, equal to f naught less than f1 less than f2 less than dot 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 less than f. Oh no, s. Sorry, these are s. This is s. Where in s are the the parameters which are the loops. S1, S0, S2, S sub m, which is equal to 1, of course. And also, one of these would be the femboys, and one of those would be another pair of femboys. 0 equals t naught less than t1 less than t2, so dot 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 less than t sub m. Yeah, equals 1. So that f of s minus 1 sub s, f of this interval, or the image of this interval, is I cross t sub j minus 1 P sub j is in a single A alpha. Okay, so suppose I have all these loops here, which are stand-ins for a bunch of loops that are said to be similar under concatenation. There is a path homotopy, so it is somewhat like a while ago, but this time we have a space of paths, minus 1 onto x, such that, well, these things hold. Okay, and by the same compactness argument, we can partition each interval. This one is probably here from here. These are parameters of this first one, and then these are parameters of this second map here. So, yeah. And so that partition fixes this image in a single, subset of the cover, or any covering, or any subset of the covering that covers X. And the picture for this would be this box, which is precisely 0 to 1 cross 0 to 1. Then we divide it into, this is the partition, and then we map that onto X via big F. So this is a space of femboys, and then we separate them, or we break them up into small sets, and then we map those onto X. And the properties here hold under that F. Okay, now the hypothesis that we want to prove in order to prove 2, given this information, is that, our hypothesis is that oh, we have run out of time, but we're close to the end of the proof, is that triple intersections are path connected. By small perturbations. And a perturbation is just a small nudge somewhere. So what we want to show is that given our triple intersections and everything we've had thus far, if we push them a little bit, they will still path connected. And obviously they will. We're not punching a hole in here, we're just shifting things around. Okay, so the first art, what we want to do, this time we're going to use pictures here. So I have my thing a while ago, my box of points. A box of stuff. And what I'm going to do is I'm going to shift them. Such that these vertices don't meet, or the vertices of all of these don't meet at the same vertex. So this is our perturbation, and we want to show that everything here stays path connected no matter that perturbation. So I believe that would go 0, 1, 2, 3. So we only do the perturbation with respect to the y-axis, I believe here, or the x-axis. So it would go like that. So it looks like a brick wall. It looks like a brick wall and so on. And then we're going to label each of these guys 1, 2, 3, 4, 5, 6, 7, and so on and so forth, up until so. So the ordering goes like this, and then like this, and like that, and like that. So the last one, which is 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 there. So it goes like this. Oh, you guys get the idea. Okay. Or, sorry, it goes like this. 7, 8, 9, 10, 10, 11, 12, 1. Oh, no, sorry. 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think 16, 16, 16. There, 16. So it goes like this, like that. Just like that. That's how we order them. So I'm gonna let for each, so these are labels. For each index, 0 less than I less than n times m, wherein nm is of course the last square that we label. Let gamma sub I be the word obtained by f restricted to the path from left to right that separates the first I boxes. So restricted to the path from left to right that separates the first I boxes. So say for F0, I'm gonna make this more cleaner, make the picture more cleaner. So, okay. I wish I had a colored marker right now so that I could identify these things, because we're gonna trace out a bunch of paths here. Okay. I don't know why it's 5. Okay. So I think it's gamma. That's meant to be gamma. Okay, in my notes. Okay, so this small thing is gamma sub 0. This small path 1 to 3. Gamma sub 0. That's the first example. Now, the second here, these two paths over here, I'm going to specify just yet. I think it's gamma 9, I believe. It's practically the same as tracing out any path. So these two are mapped onto x naught via f. Okay. Okay, the next one is psi, not psi, gamma sub 4. Oh no, this is not gamma 0. This is some new sort of path traced out, which I will call psi sub 0. Okay? And then gamma sub 0 is equal to f, restricted at psi 1, which is the bottom edge. And then gamma. That's psi. Gamma sub 4 is equal to f restricted at psi 2. What's psi 2? Psi 2 goes like this. So first go up and stop at this vertex at 4, and then go this way, go down like this, and then go. So it separates these. So it's psi 2. And so f restricted to psi 2, whatever the heck, it's basically the map. So these two are maps, right? Which is f restricted at those places, basically. Okay. So, all right. Each vertex lies in at most 3 rectangles, which corresponds to 3 open sets. So each of these rectangles correspond to an open set or an intersection of open sets, A alpha, B alpha, and A gamma. So this vertex lies over here in 3 rectangles. This vertex over here lies in 5, 6, and 3 over here. This vertex over here lies in 4, 5, and 1. This vertex lies in 1, 2, and 5. and this vertex over here lies in 2, 3, and 5. This vertex over here lies in 8, 9, and 5. So really what our goal in the beginning in making these partitions, or making that small perturbation, was to sort of prevent there to be there be two separate edges basically, or no two vertices meet. Okay. So let G be a path in the intersection of A alpha joining F vertex with X naught. We can factor each gamma sub I, each of these, into a word with each letter corresponding to F restricted to an edge in the grid joined to X naught using the path G for the first vertex and the second vertex. In this way, we have a sequence of factors of F starting with F naught and ending with F prime something something. These are all equivalent since passing from gamma 1 to gamma I plus 1, or no, gamma I to gamma I plus 1, just includes path homotopy in a single A alpha. So I'm going to rewrite that. So I'm going to first erase this picture, and keep the picture in mind, of course. And let's write it out. So each vertex, so this is the last stretch of the proof. Each vertex lies in at most 3 rectangles. Still recording? Good. Which correspond to 3 open sets, which is A alpha, A beta, and A gamma. Okay, let G be a path in the intersection between these 3. So a fine line of femboys inside these collections of femboys, which we claim to be part of an entire set that covers our original space, joining. So it's a path that ends and terminates or starts and terminates at F vertex, F at the vertex, and the base femboy. No, width, sorry. So it combines these two into one, or makes an equivalence relation with them. And then, yeah. So it's practically almost, yeah. Okay, so I have a vertex with X naught. We can factor. I know we're a bit over time, but keep in mind, just bear with me. We can factor each gamma I into a word. Into a word with each letter. So a concatenation, right? Corresponding to F restricted at an edge in the grid joined to X naught. X naught using the path G for the first vertex. For the first vertex. And the second vertex. In this way, we have a sequence of factors of f, or the original f, starting with f1 dot fl and ending with in the primes f prime 1 to the dot f prime of k, sorry, not l, which are similar. These are all equivalent since passing from like we said a while ago, f1 the dot fl is equivalent to f prime 1 the dot f prime of k. Since passing from gamma sub I to gamma sub I plus 1 just includes a path homotopy in a single and there, that's our proof, or the end of the second part. Yeah, I know we are a bit over time, but just take note of this and all that. Take note of the argument as well, how similar the two are. It's amazing how they are. So that will be it for this lecture. I won't be able to go deeper into applications just yet. I think that will go in the next lecture. So yeah, that will be it for this lecture, and this is a good place to stop.